Hello and thank you for joining us for the latest AMS webinar with Comau. My name is Nick Holt and I'm editor of Automotive Manufacturing Solutions. As you know, the development and demand for lightweight engines has brought into sharp focus technologies that have been waiting in the sidelines. Thermal spraying for cylinder boards is one such example. Today, Paolo Rosa, who is Comau's product manager for powertrain thermal spray systems, will be demonstrating how Comau combines its expertise in welding systems, metal cutting and manufacturing systems with its thermal spraying technology to deliver efficiencies in fuel, weight reduction and costs. Paolo, who has a degree in materials engineering, came to Comau from automotive manufacturing, where he took a lead role in the development of alternative liner systems. He's one of the original LDS patent inventors and has 4 patents in thermal spraying. Now, before I pass over to him, I'd like to remind all of you in attendance today to draft some questions which Paolo will answer in the Q&A session following his presentation. Please ask the questions by typing them into the box in the lower right-hand side of your screen. If you happen to experience any technical issues during the session, please also type these into the Q&A box and our team here will do their best to sort these out for you. We hope you find this webinar stimulating and informative. And I'll now hand over to Paolo to begin the presentation. Thank you.
Hello everyone. As I go through this presentation, it's a bit of information, so bear with me. Some of the speed of the slides are more reference than discussion points, and then we'll have some discussion points at the end of the presentation. Here at Comau, we have done significant work in the last 12 months. We have partnered with Flame Spray Industries to bring their technology to manufacturing. Our product line will be called Smart Spray Comau, which will provide a full enclosed system ready to go into manufacturing lines, and we'll review that at the end. We'll go over the state of the art of the automotive and commercial programs, the advantage of thermal spray liners for powertrain, the status of the Smart Spray with PTWA here at Comau, and we'll review some of the solutions we have for manufacturing, block design, and recommendations for implementation of a bore spray coating to replace cast iron liners. Most of you are familiar with these two vehicles, the GTR and the GT500. Both of these have been in production now several years, and each of these are using PTWA in production. Why is automotive so interested? As most of us know, most companies now are pursuing every means to reduce fuel consumption, and one of the biggest contributors are the losses due to the engine, in particular heat losses, combustion, pumping, and friction. In those areas is what we'd be focusing mostly on, but just for reference, we do have reference technologies such as multiple MDS or multiple cylinder deactivation systems. Roughly cost a customer or supplier $150 for a unit to put into an engine. Start-stop usually contributes about an additional $80 to an engine as you add the larger starter motors, change the bearings to higher grades. So this kind of gives you the idea of how much is going on in the industry in terms of people investing into the product for commercial usage. What we found here with efficiency and combustion, we have areas where we're losing the energy created from combustion by exhaust losses, cooling losses, mechanical, radiation misfiring losses, pumping losses, and what you see is in that combustion zone we have a theoretical efficiency improvement from BFCs. This information was taken from a Mazda presentation back in 2012, and a theoretical limit for combustion ratio versus efficiency improvement has a theoretical limit is the pink curve. And what happens is really in the real world we end up coming to a wall typically around 12.5 to 13 where we just can't get past that. Part of that is due to the temperature inside the cylinder bores initiating radiation or misfiring. What we found with thermal spray is by improving the thermodynamics within the cylinder bore area, we can slide the knock limit curve to the right and upwards, and enabling a higher compression ratio in some applications, or taking advantage of the friction losses. In terms of the field now, there are multiple engines that have made it into the field. Both Daimler and BMW have been the largest producers now of thermal spray engines, but we've seen a lot of shift from sports cars now to mainstay vehicles. As well, in the commercial market, what we're finding is companies pursuing technologies to allow them to increase their EGR. One of the problems with increased levels of EGR inside cast iron blocks is corrosion of the cast iron. By using a coating system and staying even with a cast iron block, you can replace the wear surface with a corrosion resistant surface, inhibiting corrosion, as well as being able to reduce your friction by the inherent porosity of the coating. And then of course now you have a harder coating in the surface. It increases the durability of the engine. Reman is also an area that a lot of people have been pursuing. Part of the reason here is you're able to take a fairly expensive casting, rebuild it to original specifications on the cylinder bore and other surfaces, and be able to recoup the cost of the casting. In particular, it's very active in industrial and off-road applications. The benefits for thermal spray, as I briefly talked about, there's really three key areas. One is the replacement of the cast iron liner within the coating in the design itself. So you have a cost reduction here. A typical liner costs roughly $4 cast in to an engine block. You can reduce that and replace a four-cylinder block with roughly $2 worth of material and spray time. Of course, you have to compensate that with your investment, but it's a significant cost savings on an engine block. Weight reduction, because we're able to package with a smaller liner versus a large cast-in liner, you're able to reduce the length of the block, which it has several intrinsic values, reducing the overall length of the engine. Improved durability, we are talking about replacing cast iron with a graphite phase with a hardened steel with inherent porosity that allows us to reduce the friction, but also as well as reduce the wear on the surface. Going into step 2, or item 2, is the improvement of thermodynamics. We have NVH and knock, friction reduction, able to tighten up piston clearances, reduce knock potential from hot spots due to cast iron liner, which is usually caused by variation in the position of the casting. Because of the improvement in thermodynamics, there are significant improvements in fuel economy and emissions. Packaging, of course, but the biggest benefit is there's no gaps between the coating and the block surface. This is intrinsic to the process, as well as the only way, if we have a gap, we don't have adhesion of the coating. Improvement in tribology, because we are going to a harder phase material. Typically it's a mixture of oxides as well as martensite and bainite. Produces a fairly robust wear surface. On top of that, the intrinsic porosity within the process allows us to contain and create pockets of oil on the surface, which really literally help slide the Striebeck curve to the left, putting us directly into hydrodynamic immediately versus having a lot of mixed mode. Benefits for that go on and on, anything from start-stop to reduced friction, of course. In terms of investment, this is just a rough slide. It's not looking at any of the other additional investment such as the rough honing that we would recommend, or any changes to your CNC process. But what we do see is, as you produce more and more bores per year and achieve a volume upwards of 100,000 bores a year, you start to see a payback period close to 2 to 3 years. While it's not a one-year target that most OEs have, it is fairly significant because the process is flexible and it isn't dedicated to one bore size or bore length. So it gives you a piece of equipment that you can then retask for the subsequent models and such. From a paper from Nissan back in 2007, they documented and showed that they were able to reduce their bore temperatures by 20 to 50 degrees depending on the operating range they were in. They were able to fit a water jacket between the liners. I believe on the GTR they have a 13 millimeter bridge between the bores, and in that they have 4 millimeters of aluminum, 3 millimeters of coolant, and then another 4 millimeters of aluminum again. So that allows them to really keep the engine much cooler, improving the knock limit, allows them to attain powers that they couldn't do with a pressed-in liner. When we talk about the thermal conductivity, a lot of that, just looking at the ideal law, shows that if we were to go from the conventional 2.5 millimeter gray iron, which has approximately, for the system, so for a wall thickness of 8 millimeters, you have the system thermal conductivity of roughly 74 watts per meter Kelvin. If you go to a 100 micron coating with a 4130 in PTWA, it's roughly at 94, 93 watts per meter Kelvin based on just the ideal thermal conductivity law. So it gives you the ability to really see how much cooling you can benefit just by reducing the thickness of the layer. As you get closer and closer to 100 microns, the variation between different materials becomes less of an impact to the overall structure of the wall. As you go into looking at modeling that, what you can see is just on a baseline study, we were able to see that liner temperature dropped 16 degrees Celsius. A significant improvement. The biggest improvement was dropping the max temperature to below 190, particularly in the bore bridge area. Definitely a significant source of knock for most engines. If we look at what that effect is overall in the engine, what was found in a Chrysler paper in 2000 presented to the DOE was that you had a change in the cam phasing by 7 degrees at idle or close to idle, with an improvement all the way up to about 5,000 RPM. That's a significant benefit because you're not removing the camshafts as much as you were before. As you go into a Ford paper, again, similar performance reductions they've seen. Nissan reported the lower temperatures, and that showed for Ford a 28% reduction in idle in terms of the average torque required just to turn the engine. Same thing, that improvement was duplicated over 2 different tests. They found that improvement to continue on all the way up to about 3,600 RPM. We'll get into the details, but really it's this small inherent porosity that's on the surface that provides the ability to go into more of a hydrodynamic state with the rings and piston to the liner than just having a smooth surface. Again, that improvement allows a significant reduction in fuel consumption. Again, to the paper from Chrysler to the DOE in 2012, you can see they had a improvement of up to 27% in the low mean operating range, where you typically are with an engine between 1,000 and 2,500. This is significant. It contributes to about an improvement of 3% in a vehicle, which in this day and age is pretty hard to come by. So what are the different technologies that people are investing in, what we're pursuing here? The first one that went into a production field was the APS from Sulzer-Metco, their Sumi board. It was great. It opened the door. It has significant issues in terms of temperature, cooling. It requires a water cooling of the nozzle. It has a plasma arc jet that's around 24,000 degrees Kelvin. You are inserting a powder stock into that jet. So the powder effectively goes from a room temperature to a liquid to semi-solid or even solid, depending on how it's shadowed within the jet. But it's very consistent porosity and very consistent in terms of surface finish. One of the smoother ones of all the applications. In plasma transferred wire arc, we have an arc temperature of roughly 7,000 degrees Kelvin. We use a cathode to create a plasma field between that and the anode, which we use as our consumed wire. We don't use this for propulsion. It's only used to melt the tip of the wire. What we have is an ionizing gas stream, which is the blue curves, the blue lines that you see coming in through multiple orifices around the plasma field. This is what creates the atomization and the acceleration of the particles towards the surface. We can flip between different gases depending on which type of coating people are preferring. Typically, though, we are using a compressed clean dry air. As I said, it was been in production since 2007 with Nissan and 2010 with Ford. The LDS, or twin wire arc, has been in production since 2005. Basically here you have two wires, one acting as the anode, one as the cathode. You're creating an arc between the two. It has roughly a 3,000 degrees Kelvin arc, much smaller. You end up with slightly larger particles here. Your gas jet is typically a nitrogen based. This allows them to pick up the wire and maintain a stable arc. Particularization again and acceleration of the particles is created by the gas jet that's fed from behind the arc point. Overall, when you compare the different processes between the nanoslide and the smart spray, both have a very high operational and material usage. Deposition rates on PTWA are around 92%. In terms of the ability to spray different materials, both nanoslide and smart spray use a wire-based material, while the the nanoslide uses a 1080 or a high carbon steel. The smart spray, with using a compressed air, can use as low as a 1010 and any high carbon or modified alloys. Cycle time for a nanoslide is typically 30-ish seconds. At 85 amps, we're around 60 for a 84 millimeter bore, 4-cylinder. At 150 amps, we're just under 40 seconds. In terms of running time and changeover time, the LDS is limited by the wire that's carried on board. Smart spray we feed from an external wire supply, and we're able to butt weld the wires, so we never have to shut down for a wire feed or change. For us, the time that we have is really the interval to change the arc torch, which has a life depending on how you're operating. If you're operating with a constant start-stop operation, it's 70 hours, and it pursues up to 100 plus hours if we run continuous on the torch life. In terms of surface roughening technologies, this is really a package that everyone's looking for. Most customers, some of the early adopters have developed their own. Some of the new to the market are looking for assistance. Some of the first technologies that went into the market are grip blasting, which is one of the oldest surface prep technologies. It creates a very random and rough surface. It's difficult to measure and count and identify the quality of the surface without an adhesion test. One of the more major issues for production is the cleanliness. Grip blasting tends to create a lot of statically charged fines, and these tend to adhere to the surface quite well and make it difficult for cleaning and coating afterwards. The second process that's really taken off is water jet. This process produces a very clean and complex surface, also difficult to measure and assess, but it has a very high quality surface and very high adhesion results. The one shortcoming with water jet is its ability to ablade and open up any casting issues, particularly in die cast. But those are things that can always be evaluated and developed. But for now, the trend seems to be moving towards, from our side at least, to a mechanical surface roughening. In mechanical surface roughening, there are the first one in the field was Nissan with the GT-R. They created a mechanical surface that had a break in it, effectively creating something between a machined and broken surface with very good adhesion results. This kind of brought everything back up that's been published since 1953 regarding cutting a groove and deforming it. So this has become a mainstay for most people going into the market, is looking at a process of cutting a groove and deforming it. The Hansel and Gehring process, which I didn't mention here, both are a threaded type process. They will cut a groove and then deform it within their same process. Hansel has it integrated into their tooling. Gehring has a separate roller. Ford has developed their own process, and it's near production, and it allows them to do an interpolated circle, and this is kind of where I see the new future going, to a prepped surface that allows you to selectively machine areas. One of the other areas that's used often for prototypes is called Braunschweig. It's a tool that requires no post operation. The undercuts are created by the tool itself. The tool here is also a thread formed tool, so it'd be chased through the full thread, so it really limits the application and requires a clean exit and entry in the bore. The nice thing about the mechanical prep surfaces is you can easily measure these surfaces with a profilometer. There's a lot of question about, well, how do you know about the undercut? The profile that's created by a well-prepared surface is definitely different than a surface that doesn't get prepared well, and I can give you an example of that in a moment. In terms of surface preparation, as I said, there's several different technologies available in the market, one of which it will be coming eventually. We've been testing and evaluating it. It's not in our area to license it. We plan on providing that as a solution to our customers. It's based on similar technology as the other mechanical ones. It will allow us to do a concentric selective bore prep if we want, or a full bore prep. One of the issues most people have are how do we assure adhesion. As we've gone through and done a lot of mechanical testing, we can find that in our test samples using a standard pat gauge, or not pat gauge, pad gauge, we can pull up an adhesion sample right off the coating and measure the mechanical bond strength using a simple button that's glued to the surface. For most of the results that we see now, typically adhesion properties for any mechanical prep are above 45 megapascal, but once we have a good tuned-in process, it's consistently over 50. I know there's been a lot of talk in the market about what the limit for your lower adhesion level should be. Roughly 21 to 23 megapascals is the load created by the honing process. And from my opinion, Volkswagen's been in production for many years with coatings below 20 megapascals. So from our side, to make calculations in terms of capability, 20 megapascal is sufficient lower limit. If you start to pull it up, it just makes CPK calculations harder. Most processes stay well above that limit. Now, these are just reference numbers, but everything that have been evaluated has produced adhesion results around the 50. These aren't guaranteed results. It's just giving you an idea what the difference is between a grip blast, water jet, and the various mechanical roughening processes. To give you an idea what the Braunschweig looks like, the bottom left image gives you a cross-section and shows you how the dovetails are cut into the surface prep with the coating sitting, where's my mouse? With the coating sitting on top and the aluminum below. The selective prep process being evaluated can produce a grooved area, and then through mechanical deformation of the positive portion of the grooving, we get a dovetail formed by the deformation and providing sufficient adhesion results. When I was talking about in terms of how to quickly verify between different surfaces in terms of prep. This is an example of a Braunschweig, and what we're looking at is the wave profile as of the prep surface versus a prep surface that ran 2% out of speed. And you can see that even with a good tool, a bad part could have been produced, but geometrically the numbers are completely wrong. Height-wise is actually about half the height of a good prepared surface, as well as the waveform or wavelength is much shorter. So these are numbers that are easily calculated and measured and compared between different samples. In terms of coating characteristics, we have the ability to spray, like I said, with air and nitrogen with PTWA. The advantage of spraying with air is that when we spray a low-cost alloy like 1010, we're able to create a metastable woostite or FEO. This provides a lubricive and wear-resistant phase. The FEO fractures across the basal plane and providing a very good lubricive nature to the coating. If we were to spray this without nitrogen, we would create a very fine level of oxide. A fine level of oxide between particle splats. In terms of the basic coating, when we do use a 1010, it's a low phosphorus, low sulfur, 0.6 manganese wire. It's very compatible with piston rings. Typically the porosity range is 2 to 4%. Nominally it is around 3%. The performance that we see here can be improved if we increase the porosity to 4 to 6 range, which is easily controllable within the machine. The flexibility of the system, like I said, we can spray a 4130. The difference is within the hardness created by spraying 4130 or 1010 with air changes based on the carbon content. So with the higher carbon content and alloying phases of 4130, we get an increase of approximately 60% in hardness. Part of this hardness issue is what creates post-machining issues for boring, and why we recommend going with a honing. The porosity is fairly well random. It's almost a random homogeneous distribution. So the coating will have the similar porosity throughout its depth and across the length of the coating. In terms of manufacturing, a lot of questions are, well, can we not do that much sooner in the surface preparation in rough or even at a sub-supplier? Currently our recommendation is to focus in on the final machining, or if you have a very stable locating system, then you can do it much farther upstream. The main reason for this, and it has nothing to do with the PTWA in itself particularly, is when you're targeting a 100 micron surface, you have to take significant care on your locating features so that your true position for your bore centers, which is going to be set by the surface prep, is maintained throughout the process. So the sooner you cut that surface, the more care you have to take through the process in maintaining that position. In post-operation, after coating, if you're doing a non-selective prep, so where you've actually coated through the bore into the crankcase, we found that a high-pressure wash has the ability on die cast to easily remove it. On sand cast, it would be recommended to do a shadow mask with a small amount of jet washing. It definitely allows us to remove the coating throughout the bottom area without delaminating it into the bore. Some of the changes that would be integrated into the block design, typically the chamfer at the top is placed in prior to boring. This would be recommended to be done after coating process because we would like to have a square entry for the surface prep as well as the coating process and have that cleaned off. Again, this is only if we're talking a full bore coating prep. Similarly, at the bottom of the bore, typical applications have a blended chamfer into the bore. It's recommended to put in a step that's at least 85 to 90% of your target coating application. This will allow for a significant break point at the bottom of the bore to minimize any chipping or breakage into the bore area from the coating to the non-prepped surface. When I mentioned earlier about a mask tool, what we talk is a shadow mask would line up within the bottom millimeter of a bore. The one area that we can't get masking easily into is the over the mains and the breather passage. So in this area, they'll be required jet washing. The other areas of limited remachining and cleaning up of the hone over travel is all that's required. When we come to bore tolerancing, the reason I mentioned our recommendation is to put it in the finish zone is due to investment. If we were to apply the coating much sooner with the typical bore tolerancing, I would have to change my finish coating target to about 355 microns from 150 for an example. That would change my applied coating significantly to compensate for the additional coating, and as such, the result changes the coating cycle by a third, increasing it. This then, of course, increases your investment by a third by adding additional equipment or capacity required. The reason for some of the roughness, you may be wondering why our target coating finish after hone is 150 or 350, and we're applying approximately 400 microns more. With a mechanical surface roughness, the profile will get translated through the coating as well as the inherent surface roughness of the coating. So that compounded fact creates a typical surface roughness of around 360 microns, which need to be coated sufficiently to be beyond your final machine surface. So compensating for bore tolerancing as well as coating tolerances is the reason why we target an additional 400 overspray. The first generation coating cell that was created by Comau at the beginning of this year and has been delivered and running manufacturing trials was a simple concept. Originally, gantries were evaluated, but due to the cost of investment for the gantry into the cell, it was decided to go with an enclosed robot system. The robot system gives us the flexibility to do several different things, as well as torch changes if we have secondary wire feeds, the ability to move to random locations within the cell if we need to, such as in this picture here you see a torch changer in the bottom. The basic layout has your power source and control panels in the back, and you'll notice there's two dust collection tubes. The lower tube is actually a returned recycled air for the cell. It is flown into the bottom of the case and flown up around the block. This helps to cool the block as well as direct any of the overspray, and it helps to minimize any overspray in the crankcase side of the block. The upper tube, here shown in the original concept with three tubes coming to the top, are the suction phases, and these provide approximately 5,000 CFM of suction to pull out any exhaust as well as overspray at the top of the blocks. They'll go out to a HEPA filtered dust collector and return. The return gas pressure or air is roughly 4,500 CFM, so that we maintain always an internal vacuum inside the cell to reduce any gas escaping from the cell or fumes. What you see here is the basic unit has been constructed and was prior to shipment. We have installed in this unit the ability to integrate with a Technar. This allows us to do spray monitoring at a stationary station in the center of the box here in the V. This newer cell has eliminated the passage, and we've gone to just an entry point. The nice thing about having a Technar on base is it gives you a checkpoint that you can check roughly the life or stability of the torch as you're running. And I'll go over this operation video here. The original video was created for a manufacturing show, so what we'll have is a full video starting from the loading and unloading, some of the features that we've gone through, both with our partner Flame Spray and some of the customers' desires. The cell itself has the ability to be gantry or front-loaded, whether manually or by robotics or automation. The cell also has the ability to interface with a barcode reading system and track every engine block coming through. So in the far right side, which is covered by the robot currently, was a barcode reader that each block was scanned prior to loading. The doors close, and the reason that we do that in manufacturing, we'd be using a continuous torch operation. The reason for that is the torch arc life is less than, there's less usage of the cathode if we don't keep igniting it, and really the torch life is dictated by the cathode and the buildup within the torch. So what you've seen is we start both torches in a stationary position and spraying down into the suction system. Once we start spraying, we'll move to the coating locations, do approximately 4 to 5 passages depending on the bore size and bore length, and then repeat that for the following cylinders. In a manufacturing process, we'll keep the torches operating in between part change. And this, for a prototype cell or initial prototype runs, we weren't running as often, so we were shutting quite regularly. So our second generation, which we were already in the process of producing here, has gone to adding a larger table to accommodate some significantly sized blocks. We've also reduced the size of the power supply when we use an 85 amp system. But one of the more significant changes is that we've added the ability to produce hydrogen on board. The reason for this is due to the regulations around pressurized hydrogen. It's much simpler for us to provide hydrogen on demand to the cell and be well below any requirements for permitting. It makes it a much simpler system and allows us to provide a simple package to a customer without a large impact to their manufacturing facility. The first one that you saw on the previous slide was a single torch system. This is a dual torch system. What you can see is that we've changed the suction system to a very large cross path, and it helps reduce and capture more of the dust that's collected. We've also then had to move the inspection station below, as well as in some trap doors. It allows us to help capture and limit the exposure of the table to any buildup. As I mentioned before, we've been able to integrate the AccuSpray from Technar. The ability to do this allows us to, on a regular basis, whether it's every 100 hours or every hour or every 20 blocks, to be able to bring the torch to an inspection location, run the torch, characterize and record the plume, put a feedback back into the system if there's any change in the plume direction, compensate for changes, and then continue, or even predict torch life and be able to ask for removal or replacement of the torch. As I mentioned earlier, we've gone to what we call H2 on. This eliminates a lot of the IFC and NFPA requirements. We only have 4 to 8 grams, depending on which units we're using, of pure hydrogen on board, well below the international limits of 100 grams. This eliminates a lot of the on-site storage issues and gas delivery issues. By having the hydrogen located very close, you're able to control and mitigate a lot of the issues there. When we move on to inspection, we've had a lot of discussions with several customers. There are 2 inspection systems that we've been evaluating, one for post-honing and one for measuring prior to. We're still in the process of developing these, but they show significant merit for the applications, giving us the ability to characterize the porosity after honing, which is not an issue. We're not using it for characterization or control of the process. It's more just a quality check. We do control it quite accurately through the parameters in the cell and maintain those. The other area that we're targeting is the ability to inspect the rough castings, the roughened surface, and also the post-coating. These will be going through trials soon, early next year, and hopefully we'll have a solution by the summer. As Comau, we have the ability to provide a full system. We've taken and leveraged some of our technology from our CNCs and our robot systems to create a well-operating and much more efficient package for providing a coating to systems. Later this year, or early next year, pardon me, we'll have the ability to provide everyone a nice quick peek to an actual production cell. We'll have that here sitting in our facility for customers to review. In terms of our background with our partners in flame spray, we are able to bring to people 50+ years of thermal spray liner coating experience. We have the ability to prototype engine blocks up to 900 pounds down to 65 millimeters in bore. We have the ability to hopefully early next year down to 37 millimeters. Production development, again, we have a broad experience in engineering and handling this technology, so we are able to do and answer a lot of these questions. We are expanding our customer support base. We now have individuals in Europe and in Asia who are being trained and learning the process, as well as we're expanding our ability into Mexico. With that, I'll open the floor to any questions.
Thanks, Paolo. That was a really interesting and very thorough and detailed presentation on the offerings, powertrain offerings from Comau. And we do have some questions for you. So I'll do my best to forward them. They are quite technical questions, so I hope I get these right for you. First question, I believe, is from a colleague at General Motors, and the question is, can you explain the difference between PTWA1 and PTWA2?
The first PTWA concept cell that we had for Smart Spray was a much larger enclosure. It used a separate controller versus the new system. We've integrated everything into the robot controller. The nice thing about the robot controller is it's fully integrated with the safety cells. By reducing the control systems, we're able to increase the processing speed, as well as the cost of the system is reduced by focusing everything into the control system from the robot. The second item is we've improved the dust capturing system significantly. We've changed the chassis. We're approximately 3 feet shorter in length and about 2 feet shorter in height. So it allows us to put this new system onto what's called a double drop trailer. We're still pursuing to see if we can make this smaller and smaller to make shipments much easier. If that was the question, the only other reason item I can think of is if you're asking 1 and 2, we have a single torch system and a dual torch system. The dual torch system allows us to coat 2 engine blocks at a time. The reason that we do 2 blocks instead of working 2 torches on 1 block is the ability to mask between the 2 torches so that we don't spray accidentally into the second torch. Within the same package of an LS100, we can package 2 torches and make it an LS200, and that provides effectively twice the output.
Thanks, Paolo. Another question here. I believe this is from one of our colleagues at TVS Motors in India. The question is, what are the prerequisites in terms of surface morphology for the thermal spray to be applied?
If we're focused on aluminum, on the aluminum side, the surface morphology requires an undercut rough surface. If you had a rough surface with no presence of undercut, any type of area where the surface, the coating could lock to the surface, it won't adhere properly, and you'll get an adhesion rate in around the 10 megapascal or lower. In terms of surface prep with vertical lines, so we've through testing we found that if you're over 200 microns in depth of a groove, it doesn't require any undercutting. It is sufficient in terms of surface contact to reduce the mechanical interlock. Then, of course, the biggest thing for us is cleanliness of the surface. When we talk about cleanliness, we require the surface really to be dry. Any residual water or coolant will cause a local steam pocket that then will create an area of delamination. The other area is any particulate or chips that are left on the surface in mass will cause an issue. However, we've done testing with what's called MQL, or minimum quality lubricant, and dry machining, and the fine chips that are created, or the stringers that are left behind, with the pressures that we're running through the torch, we're able to blow them off, and at the temperature we're spraying and the size of those fines, we're able to eradicate them fairly easily without any detriment to the adhesion. Really, what we're looking for is ensuring that the surface is clean and dry of any contaminants, particularly organic or water.
Thanks, Paolo. Next question, what's the minimum bore diameter possible for using the thermal spray or applying the thermal spray?
The current torch design from flame spray that we've been using is capable down to 67. I'd prefer to stay not much below 70. Once the package starts to get a little tighter, it's a little hard to fit in. However, flame spray has developed what they call a mini torch, and it gives them the ability to get down to approximately 37 millimeters.
I'm just going to see if I can get the context of this question. It's sort of 2 questions. Is it an aluminium metal coating? I'm not sure if this is discussing the actual coating. It is asking what the coating material is that you're using for the spray.
The coatings that we've been using are typically iron-based. The reason for that is for the wear resistance. Once you start dealing in film technology or coatings in the 100 micron range, the impartial or the impart of the thermodynamics is really reduced. So at that point, trying to focus on using an aluminum provides no benefit. There is the ability to test cord wires. Such testing has already been completed, and you can spray some fairly interesting metallic materials, even composite metallic materials. But for the most part, everything that we're doing for production tends to be focused around iron-based alloys, in particularly 1010 or stainless.
Thanks, Paolo. This next question, I think the question refers to the the sort of horsepower capacity of the engine, or the horsepower output of the engine, is there a minimum or a maximum horsepower capacity of the engine that the spray coating can be applied to?
No. The spray coating is really just a wear surface. It does not impart any structural requirements to the block. That would be required by the block design. The coating itself is really just a wear-resistant surface providing a tribological interface to the piston and rings. So at that point, pretty much the sky's the limit.
Thanks, Paolo. Question here, interesting question. Two parts to this really. How does it compare to a Nickersil type coating? And secondly, second part is, how suitable is the system you've been describing today for low volume or prototype production?
Okay, taking the first part, comparing it to Nickersil. Nickersil is a much thinner coating. It's a little more costlier in terms of application in respect to a capacitized volume. When we start talking to a prototype volume, I haven't done enough requests for Nickersil to say if I coat one block, is it sufficient? In terms of performance, several of the reman applications actually replaced Nickersil coatings with the thermal spray coating. In particular, some of the first applications with PTWA did exactly that. So in terms of Nickersil, I think you'll see a better wear performance. Friction improvement is definitely, in terms of thermodynamic growth because of piston and bore, is similar between the two. The benefit the thermal spray has over the Nickersil is the inherent porosity in the coating. By creating these small pockets of oil on the surface that the ring covers when it travels over. So the typical diameter on these porosity is around 20 microns. So once the ring travels over that surface, that oil that's trapped in that pocket goes completely hydrodynamic because it has no place for the pressure to escape to. Unlike a honing pattern or an open surface, the pressure is immediate. So you have a hydrodynamic point under the ring at almost every speed. To your second question for prototypes, it works well. At that point, you'd have to look to a lower cost cell than the one that I've talked about here. But depending on the volumes, it can be easily discussed. I do have some local partners that are planning to branch out in that range. I think it almost depends on where you're located to talk about prototypes.
Thanks, Paolo. A question here. You may have already sort of mentioned something along these lines in the actual presentation, but the question is, has this process been applied in agricultural engines?
Right now, Caterpillar has 5 facilities worldwide producing these. Can I tell you if these are being used in agricultural powertrain? I don't know. They're being used in some fairly large diesels.
Okay, well, yeah, obviously that's a tricky one. We have a question here. I understand it's from guys at Chrysler. Have there been any studies of the effects of thermal spray coatings in boundary or mixed lubrication regimes for applications besides cylinder bores, i.e. sort of bearing journals, things like that?
Yes, some of the testing's gone on now. From previous days, there's some testing on connecting rods as well as crankshafts. There is some benefit, but some of it might be easier applied. Definitely for connecting rods would be another target product I'd be interested in evaluating. Connecting rods have been tested with especially the smaller torch design. You can fit in really what I like about that is the ability to reduce the size of the crank end on a connecting rod. And the same thing can be said for any type of Babbitt style bearing in the chassis system.
Thanks, Paolo. That was an interesting question, actually. The applications beyond powertrain, or beyond certainly cylinders. Question here: are there any limitations on the type of block, the substrate materials that can be used with this spray process?
Currently with the mechanical adhesion, it's focused on magnesium and aluminum for light alloys, effectively. For cast iron, typically the route to go is with a bond coat, which is typically a nickel aluminum alloy sprayed directly onto a machine surface of the cast iron, and this is how most of the reman is done today.
Thank you. We have time for one final question here, Paolo. Why don't you recommend post-boring instead of direct to rough hone?
In the current state of the industry, post-boring machining is showing a tool life issue. The hardness of the particles from the coating and the roughness of the coating tend to really do a number on cutting tools. Currently, I've seen tool life anywhere from 4 to 70 bores, and once in a while, some reports of up to 200. In terms of comparing that to a rough honing, the rough honing seems to have a tool life, at least in one particular supplier I've been dealing with, 5,000 to 10,000 hits.
Thanks, Paolo. We just have one more question here. Are there any restrictions associated with high-pressure die-cast parts?
The only restrictions, and this would go with any casting that you're applying directly to, if you're using a mechanical prep on aluminum, I'd say you can limit your porosity to about 0.7 millimeters in the ring travel. Anything outside the ring travel, at that point, you can have much larger porosity. But for die cast or sand cast, there really is no limitation. Most of the product I've been doing now is die cast.
I'm giving time for one more question. It's a very interesting one, Paolo, if you don't mind. Question is it to be understood that embeddable shell bearing-like materials can be directly applied to substrates rather than using shell bearings? It's a follow-on, I think, from a previous question.
Yes.
It's as simple as that. Okay. Well, all of our attendees can obviously follow up with any further questions they have with you guys at Comau, and I'm sure there'll be many more technical and more specific questions coming your way. Thanks very much for all our attendees for joining us today, and thank you to Paolo for a great presentation and for answering all those questions. The webinar will be uploaded into our archives and accessible in the future to all of your colleagues who have been unable to attend this live presentation. And you can access this and all our previous webinars via the webinar tab on the AMS homepage. So thanks again for joining us today, and we hope you'll join us for our next webinar. Thank you very much.